Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising SHM and this would be the second lecture of SHM. In this lecture we will be talking about the dynamics of SHM. So without losing any further time, let's share our screen. So here we go. Let's talk about dynamics of SHM. If we want to prove the motion of a system to be SHM, we need to take following steps. First, we need to locate the stable equilibrium position of the system, means the location where the net force acting on the system will be equal to 0. And also we must ensure that dF by dx must be negative and or d2u by dx square must be positive. So once we have done this, okay, we must assign that position, stable equilibrium position, as origin, or x is equal to 0 coordinates, and then we must displace slightly from its stable equilibrium position, okay, and try to figure out how much restoring force is now acting. If the restoring force is of form F is equal to minus kx, then the motion will be SHM, and omega, the angular frequency of SHM, would be nothing but root under k by m. Or you can say time period would be 2 pi root under m by k, and frequency will be equal to 1 by 2 pi into root under k by m. So in order to do that, like, let's take the simplest thing over here I would be taking is a spring block system. Okay, so in spring block system, you should realize one simplest setup I am taking. Let's say this is a block of mass m, and it is connected with an ideal spring, okay, and the another end of spring is connected to some rigid wall, and this is kept on a frictionless horizontal surface. Okay, so let's say the spring constant of the spring is k. Okay, so you must understand, like, when the spring is at its natural length or unstretched or relaxed, you can say, then spring will not be exerting any force on this block over here. So net horizontal force on this block, you can see, is equal to 0. So this definitely is a stable equilibrium position, and I must assign the coordinate x is equal to 0 to this position. Okay, so now the next thing, we must check, like, what happens if we displace it slightly. If we displace it slightly from its stable equilibrium position, let's say by x. Okay, so in that case, what would be the net force acting on this block? So you understand, the net force acting would be now in this direction, and this force here will be given by minus kx. This minus sign is because this force will be opposite of displacement, you must realize. So F is equal to minus kx. That would be this force exerted by the spring over here. And we can very well write F is equal to ma is equal to minus kx. So A, you should realize, is nothing but minus k by m into x. Okay, and previously when we were studying the kinematics of SHM, we learned that A is equal to minus omega square x for SHM. So comparing this equation and this equation, simply the angular frequency is root under k by m. Okay, so frequency also you can find out. So frequency of oscillation is nothing but omega by 2 pi, right? Omega by 2 pi. So you can write it as 1 by 2 pi into omega, that is root under k by m. And similarly, you can also find out time period. Either you can write 1 by f, or you can write 2 pi by omega also. So that will simply give you 2 pi root under m by k. Okay, so this is how we generally prove the motion of a system to be SHM. Okay, so let me repeat it again. You first have to locate the stable equilibrium position. Once it is located, assign the coordinate x is equal to 0 to that. You can assign any coordinates value, but I am suggesting you to assign x is equal to 0 coordinate to the stable equilibrium position to have easier calculation, and then you can displace it slightly from the stable equilibrium position and check how much the net force now become, whether it is restoring in nature or not. So here we have got the force as this. Okay, so this spring block system will execute SHM about this mean position with this much time period, and amplitude will depend upon like at what extreme we have initially stretched it. Like for example, let's say at x is equal to a, we have stretched and we have released from this position, means v is equal to 0 at x is equal to a. So obviously a will be the amplitude of this oscillation over here. Okay, so here this was the simplest model. Let's take one more model here. Okay, so let's take the case of a block, hanging block with a spring. So let's say this is a block of mass m and the spring constant is k, and this is how it is hanging. Okay, and this point of suspension is fixed. Okay, so now we have to find out, first of all we have to prove the motion of this block if it is displaced in the vertical direction or along the direction of spring. Okay, and released, its subsequent motion will be SHM, and we have to find out its time period. So first thing we need to find out is the stable equilibrium position. Okay, so you must realize that the spring would be stretched, okay, when this block is in stable equilibrium position, okay, such that the net force is equal to 0. So let's say this is the position when it is in equilibrium. So let's assign x is equal to 0 coordinate to this. Okay, and you must realize, let's say this is the position of the block when the spring was relaxed. So obviously if this is x naught, we can definitely find out the value of x naught over here. So you should realize that when you will draw the free body diagram at this instant of equilibrium, so mg force would be acting in vertically downward direction, and kx naught would be the spring force exerted by spring on this block. And since it is in equilibrium, so kx naught minus mg is equal to 0, or you can simply say x naught is equal to mg by k. So this is the stretching in the spring when the block is in equilibrium. Now my next objective is to displace this block slightly, let's say by x over here. Okay, and see how much a restoring force would be acting. Okay, so when we have stretched this, okay, the force that is acting would be definitely in this, or rather let's write the direction, write the force in the direction of displacement. It would automatically turn out to be negative. So if you realize at this situation, the force that would be acting at this level over here would be nothing but mg in downward direction, and now the spring force would be nothing but k times x naught plus x, because previously it was elongated by x naught and further we have stretched by x. So net spring force would be k times x naught plus x. So net force which we are writing over here would be nothing but F is equal to mg minus k x naught plus x. So now look very closely. I am writing it in rearranged form. So that is mg minus kx naught plus minus kx. I will write it like that. And you should realize this, I will term it as equilibrium force. Let's say Fe, let's term it. And this term I will name it as a restoring force. So you should realize that the equilibrium force mg minus kx naught, as we have named it, this was the force acting on the system when this system was in equilibrium. So its vector sum will be equal to 0. You should realize. Okay, that is why we are naming it as equilibrium force. And the restoring force, or rather you should say change in force, or would be this minus kx term only. So noticing that since this term is equal to 0, we can simply write it as f is equal to minus kx again. Okay, so ma is equal to minus kx, etc. So a is equal to minus k by m times x. So you can write time period would be obviously 2 pi root under m by k. So what we have seen over here, like when some constant force is acting along the string throughout, okay, it is only responsible for the changed equilibrium position. Now in the equilibrium position, okay, spring will be a little bit stretched. Okay, so only the equilibrium position will change, but the restoring force will still be same, that is minus kx. Okay, and so the time period of oscillation of this block or spring block system will not be changing. Okay, so next time whenever we are writing the equation of force, we need not write this term over here, because anyway this term is going to become equal to 0. So we have to only bother about the restoring force term. We must not bother about the equilibrium forces, because it will be anyway turning out to be equal to 0. We can have other similar situations, like for example, one another situation you can take is, let's say we have a smooth inclined plane with angle of inclination theta, and over that there is a block of mass m which is connected by a ideal spring of spring constant k, etc. So this is the system. Okay, and I want to find out first of all what would be the time period of this spring block system. Okay, so you should realize first of all, so like if this is the position when this block is in equilibrium, so there would be some stretching already. Okay, so this is x is equal to 0. So at this position over here, okay, the elongation in the spring would be definitely mg sine theta upon k over here. But the time period in the for the calculation of time period, if we displace it slightly by x, the restoring force will be only minus kx over here. I am not writing the component of weight and kx naught, etc. along the incline, because those will be the equilibrium forces we have just learned will sum up to be equal to 0. So we can simply write that, and time period would be simply 2 pi root under m by k. Another situation you can have, for example, let's say on a smooth horizontal surface, if we have a spring block system, and this block has mass m, and at the same time some charge is also there, let's say q. Okay, and there is some electric field in this region. So you must understand, like this block will be experiencing both uh, s- spring force as well as this electrostatic force over here. So if this is x is equal to 0, it would be already stretched by some x naught over here. So some kx naught would be in this direction. So x naught you can calculate, that is qe upon k, etc. But when you will be writing f, the restoring force, that would be still minus kx over here. So time period would be still 2 pi root under m by k. Okay, so this is one situation. Okay, so now let's also look about combination of springs. Previously we had only one spring in our diagram. So let's look at the case when we will be having combination of springs. Okay, so let's first look at the parallel combination. Okay, so let me give you a diagram. Let's say this is a smooth horizontal surface. This is block of mass m, and let's say there are few springs which are connected to the block. Okay, like this. Let's say the spring constant of this spring is k1 and this is k2, etc. And obviously these surfaces are rigid. So what do we mean when we say parallel combination? This is one of the arrangement. Another arrangement, similar arrangement you can see. Let's say this is the block. These are the two walls. Okay, and let's say this one spring is like this. This is K1 and this is K2. So what do we mean when we say that the combination is parallel? Let's try to figure that out. So let's say we have displaced this block by some x. Okay, so you must realize the elongation in this spring would be x as well. Okay, x1 would be x, you can say, and the elongation in this spring would be x as well. Okay, so in that case they will be exerting, this spring will exert restoring force, that would be k1x, and this spring will be exerting restoring force k2x. So in this case, the net restoring force you will be writing, that would be minus k1 plus k2 times x. Similar would be the case in this scenario over here. If we displace this block slightly by x, so this spring will compressed by x and this spring will be stretched by x. So this will also exert restoring force, that would be k1x, and this will also exert restoring force, that would be k2x. So in this situation also you must realize that the net restoring force would be of this form only. Okay, so if I write it like this, F is equal to minus k equivalent x, so obviously k equivalent is nothing but k1 plus k2 over here. Okay, so in that case we will be able to write t is equal to 2 pi root under m by k equivalent, where k equivalent is nothing but k1 plus k2. So whenever springs are in parallel, okay, k equivalent is given by summation of all the spring constants. Okay, ki simply you can write. So this is a general formula which we are having. So this is parallel combination. Please understand, like parallel combination is when the elongation or compression in each spring is same, and that is equal to the displacement of block in this case if the other end is fixed. Okay, so now let's look at the series combination also. This one is a little bit, okay, you need to focus here. So series combination, okay, as the name suggests, the spring will be in series, something like this. Okay, so this is the block of mass m, and let's say we have springs, okay, connected to each other. So let's say this is k1, this is k2. Okay, so if we displace this block slightly by say x, and this end is fixed, so there would be some stretching in spring 1 and some stretching in spring 2. So you should realize that x1 plus x2 will be equal to x over here. And also you should understand, since this spring is massless, so the spring force exerted by this spring at this point will be equal to spring force exerted by this spring or at this point. So you should realize that k1 x1 is equal to k2 x2. Okay, so that is the thing, and that will be also equal to like the force on this block over here. So that would be simply you can say minus f over here, and if you want to equate, that would be also like k equivalent into x. So solving for these two equations over here, since we know the sum of x1 and x2 and the ratio of x1 and x2, okay, you should realize that first of all, like you can find out x1 and you can find out x2 also. So x1 would be nothing but that would be k2 divided by k1 plus k2 into x, and this would be nothing but k1 upon k1 plus k2 into x, etc. So anyway, so we are interested in finding out k equivalent x. So the value of x1 and value of x2, if we substitute in the first equation, okay, so x1 is nothing but minus f by k1 and x2 is nothing but minus f by k2. Okay, and that is equal to x over here. Okay, that is equal to x. Okay, so that simply gives us you can write it as minus f uh, by k equivalent, you can say, in is equal to x, or F is equal to minus k equivalent into x, where you should realize 1 by k equivalent is equal to 1 by k1 plus 1 by k2. In more general form, you can write 1 by k equivalent is equal to summation of 1 by ki, where there would be many springs in series with each other. Okay, so this would be, then the time period you should realize would be nothing but 2 pi root under m by k equivalent over here, right? And also, like for example, this kind of question is also very commonly asked. Like for example, if the amplitude of oscillation of this block is say a, so what would be the amplitude of oscillation of this point? Let's say ap. So ap, you should realize ap, since we have this relationship over here, so ap is the basically ap will be the maximum elongation of this spring 2 over here. So maximum elongation of the whole spring is basically a, so the maximum spring elongation of this spring here would be simply k1 upon k1 plus k2 into a. Only we have replaced in this relationship, okay, we have replaced x by a and x2 by ap simply. So I hope this is clear to everybody. Okay, so now let's look at some situation when we will be having springs and pulleys also in the system. Okay, so let's look at this situation: springs and pulleys. Okay, so a few scenarios. Let's look. Let's first scenario is, say we have a rigid support and there is a pulley and there is spring like this, which is like this is the orientation. Let's say this is m, this is k. We can have another situation something like this. Okay, spring here and something like this. And one third situation we can also take. Some basic models I am taking. So this is the spring and this is the block over here. In all these situations, the mass of the block is m and the spring constant of the spring is k, and we have a frictionless, massless pulley. Okay, so in these all situations, you should realize, let's say right now they all are in equilibrium, and if we displace this slightly, the system, okay, and we want to find out the time period of the oscillation. Okay, so the idea here is what we must do. So let's displace this block slightly by x. Okay, so after displacing, we want to find out what would be the restoring force on this block over here, so that we can relate F is equal to minus kx sort of thing. So if you should understand, if this block is displaced slightly by x, this spring will be stretched by same amount F. So like the spring force in this throughout the spring or throughout the length of this spring over here would be nothing but kx only. So very clearly you can write F is equal to minus kx. So time period would be simply 2 pi root under m by k in this case. But now let's look in this case scenario over. So if this block is displaced by x, okay, so you should realize this pulley will go down by x by 2 only. So the stretching in this spring will be x by 2 only over here. Okay, so in that case, this spring force over here would be kx by 2. So the this, the restoring force in this string would be half of that. That would be, since to maintain the like the force balance on this massless pulley, so that thing is going to be kx by 4. So restoring force here we can see that would be nothing but minus kx by 4 over here. So time period we can very well write 2 pi root under m, and in place of k we just need to write k by 4 over here. So that would be k by 4 like this. Now let's look into this case. If we displace this block slightly by x, this pulley will go down by x only. Okay, so like you must realize the spring will stretch from both sides. So total elongation in the spring would be nothing but 2x. So spring force in this would be nothing but you can say 2kx this side and 2kx this side. So this restoring force would be nothing but 4kx. So F is equal to minus 4kx, you can write. Okay, so time period would be nothing but 2 pi root under m, and in place of k you can write 4k over here. So these would be the time period in these three simple cases scenario. And now let's take one more general problem in which we will be dealing with a more number of pulleys and more number of springs. Okay, previously we looked only at one spring and one pulley combination. So let's look at one general case scenario over here. Let's look closely and try to learn. Okay, so let's have this situation over here. One pulley is say here, another pulley is say here, spring, and say one spring here, one spring here, and some block is suspended like this. This is M. Okay, and this is K1, this is K2, say this is K3, and this is K4. Okay, so we want to find out the oscillation time period of small oscillation in this case. So what we got to do? So the first thing we need to do is we should displace this block slightly by some x. Okay, so in that case, like all of these spring will be stretching by a little. So let's say this would be x1, this would be x2, this would be x3, and this would be x4. These are the elongation in all these springs respectively. Okay, so here we want to relate between x1, x2, x3, x4, and x. Okay, so we want to write a constraint relationship. In order to do that, let's introduce two more variables. So this is, let's say, pulley number 1. So let's say the displacement of this pulley is xp1 and the displacement of this pulley is xp2. Both these pulleys are movable, so they will be displacing. Okay, so now we want to write the constraint relationship. So let's look closely over here. Okay, so string constraint relationship you are familiar of writing most of the time. Okay, so net change in the length of the string, you equate it to equal to 0. But in case of spring, net change in the length of spring due to the several movement of different points, okay, will be not equal to 0, but that will be equal to the net elongation. Let's say, for example, let's first write the spring constraint relationship for this spring, the K2 spring. Okay, so you should realize from one end to another end you have to move. So let's say we are moving from this end to this end. So this end is fixed, that is not moving, but this end is attached to the pulley, and this pulley is displaced by xp2. Okay, so this spring will be elongated by xp2, you can clearly say, and that will be simply equal to x2, you should realize. So that is one relationship. Similarly, we can write the spring constraint relationship for this spring over here, that is the K3 spring. So both the ends are now moving, you should realize. Both the ends are moving. This end, due to the motion of this pulley over here, this end is moving. So due to motion of this pulley, this spring will be compressed, you can say. So you should write minus xp1, and the another end here is moving by x over here. So plus x, it will elongate, and total elongation is equal to x3. So from here, what you can write is xp1 is equal to nothing but x minus x3. Okay, so that is our another relationship. And finally, we can write the spring constraint relationship for this longer spring over here. So you should I must move from one end to another end and keep tracking the change in length at each and every point. So this point is fixed, no movement, and then we encounter this pulley. So if this pulley goes down by xp1, that will stretch the spring by double of its movement. So you can say plus 2xp1, you can write. And now let's move forward. So we have encountered this pulley over here. When this pulley will move down, you should realize by xp2, this will shorten the length of this spring by 2 times xp2. So minus 2xp2 you must write. And finally, let's get to this point. So this point is moving down by x, so this will elongate, so that is plus x over here. And total elongation, you should realize, will be elongation in k1 spring and k4 spring, so that would be x1 plus x4 that you can write. Okay, so let's say these three equations we are having. Okay, so value of xp1 and value of xp2 we have already got, and when we will be substituting this value and this value in this equation over here, the relationship which we will be getting between x1, x2, x3 and x4 would be x1 plus 2x2 plus 2x3 plus x4 is equal to 3x. Okay, that is from the combination of these three equations. So let's say this is one equation, let's say equation number 1. Okay, and the second equation we can have that of force. Now you realize, please. Okay, so the spring force would be nothing but k1 x1 in this spring, k2 x2 in this spring, k3 x3 in this spring, and k4 x4 in this spring. So how will they be related? Because the pulleys are massless and the spring is also massless over here, we can simply relate the way we related used to relate tension. So you can clearly see that k1 x1 would be nothing but k3 x3 by 2 will be equal to k2 x2 by 2 is equal to k4 x4. You can write it over here. Okay, so these are the relationship of forces in the different spring. And now let's also introduce, like, let's say the restoring force is F. So restoring force will be exerted by K3 spring and K4 spring. So you must realize F is equal to K3 x3 plus k4 x4. But you should also realize that k3 x3 is nothing but 2 times k4 x4. So F is equal to, you can simply write that would be equal to 3 times k4 x4. So if you introduce this in this relationship over here, 3 k4 x4, so that would be simply, you can write it as minus F by 3 you can write. Okay, so let's say that is equation number 2. So from this equation, like for example, the value of x1, that would be minus F by 3 k1, you can substitute over here. Similarly, the value of x2 and x3 and x4 you can substitute it over here. So when you will substitute the value of x1, x2, x3, x4 from equation 2 in equation 1, what you will be getting over here is, you should realize that minus F by 3 you can take common, and inside the bracket you will be having 1 by k1 plus 4 by k2 plus 4 by k3. Okay, plus 1 by k4 you can write, and that will be equal to, you should realize, that is equal to 3x. Okay, so you should clearly understand, like F is equal to minus 9 upon 1 by k1 plus 4 by k2 plus 4 by k3 plus 1 by k4, etc. Okay, into x, obviously. Okay, so that form we were looking for, so you can convert it into something like minus k equivalent into x, where you should realize that k equivalent upon 9, or rather you should write 9 upon k equivalent, okay, is equal to 1 by k1 plus 4 by k2 plus 4 by k3 plus 1 by k4, etc. And this way you can find out k equivalent. Obviously, time period would be 2 pi root under m upon k equivalent over here. So this is one of the situations. Another situation, let me take quickly, okay, is when we have uh, mass of the spring is not negligible, means the spring is not ideal. Okay, not massless, rather you must say. Okay, so let's say we have a block of mass capital M and we have a spring. Okay, which is of say mass m over here, and this end is fixed, this surface is smooth, etc. Everything condition. So we want to find out the time period of oscillation of this system. Only difference from the previous case scenario is that we have some mass of this, comparable mass of this spring as well. So we must use the energy method in order to find out the oscillation time period of oscillation of this scenario over here. Okay, so let me introduce energy method to you also. So for example, if we displace when the displacement of this block from its stable equilibrium position or mean position is x, so let's say at that instant its velocity is, let's say, equal to v. So that is velocity of the block. Okay, so now you should realize when you will be looking at the spring, so this end of the spring is fixed, but this end, since it is attached to the block, will also moving with speed v. Okay, and let's say the natural length of the spring is L. Okay, so if we assume that the speed is varying linearly across the length of the spring, so at a distance of L, okay, let's take a small element dl. Okay, so the velocity of this element, you can say, assuming the linear velocity profile. Okay, so let's say total length is capital L of the spring, so that would be small l, uh, or rather you can say small l by capital L into v would be the velocity of this element over here. Okay, so in order to find out the kinetic energy of this spring over here, so you can find out the kinetic energy of this small element. I'm trying to find out kinetic energy of spring first of all. So kinetic energy of this small element would be half times dm times the speed of this element, which we have written it as L by L into V square over here. And dm, you should realize the mass of this small element would be mass per unit length, you understand, is m by capital L, and that multiplied with dl, so that would be, and small l upon capital L into v square. So this is dk. So when you will be integrating it from for the whole length of the spring, so kinetic energy of the spring you will be getting over here is nothing but mv square by 6 over here. Okay, so in order to prove the motion to be SHM, you should realize the energy method is simply like you can find out the total mechanical energy, let's say kinetic energy K, and potential energy of the system is, let's say, U, and that is total mechanical energy. And since this system is conservative, so that would be a constant over here. So kinetic energy of the system we will be writing. So kinetic energy of the block would be nothing but half capital mv square, and kinetic energy of the spring we have already written, that is 1 by 6 mv square. And the energy stored in the spring in form of potential energy will still be half kx square, and that is basically equal to constant. And now we can differentiate this equation both side with respect to x, let's say, and you should realize this term is nothing but half um, capital M plus m by 3 into v square. So if we differentiate both side with respect to x, so that would be 2v dv by dx, and the second term here would be half into k into 2x dx, you can write. Okay, or simply with respect to dx we are differentiating, and the right hand side will be equal to 0 over here. Okay, so this 2 etc will get cancelled, and what we will be getting, you should realize this is nothing but acceleration. So capital M plus m by 3 into acceleration is or plus kx is equal to 0. So acceleration, you can understand, that is nothing but minus k upon capital M plus m by 3 into x etc. So that simply gives us t is equal to 2 pi root under, in place of m, the effective mass, you have to write capital M plus m by 3 upon k. So this would be the time period of it. Now another important thing is two body oscillator. Two body oscillator, and let me take one simple model here. Okay, say we have a smooth horizontal surface and there are two blocks of masses m1 and m2, and they are connected via an ideal spring of spring constant k. Okay, and if we stretch this spring by a little, okay, and release, okay, we have to prove that the system will be executing SHM. Okay, and we have to find out the time period. Means both these blocks will be executing SHM, and they will be having same frequency, and their time period would be same as well. So this problem could be done in several ways, in several frame of references, and by using force method as well as energy method also. So let's take one method. So let's do this question in frame of reference of M1. In frame of M1, let's say observer is attached with M1. Okay, and he is observing the motion of M2, and he wants to find out the time period of it. So you should realize, like, when the stretching in this spring is x, okay, so according to the observer attached with m1, okay, so let's say the displacement of m2 will be x, okay, from its stable equilibrium position, that would be x. Okay, so the spring force would be nothing but kx, and this spring force will be experienced by both m1 and m2. So this would be kx and this would be kx. So you should realize that m1, the motion of m1 would be accelerated, so that would be a1 you can write, so that would be nothing but kx upon m1. So first of all, when we are working in frame of M1, you should realize the frame of M1 is non-inertial frame of reference, because A1 is non-zero acceleration over here. Okay, so when he will be drawing the free body diagram of this block, apart from the real forces, he has to exert the pseudo force. Okay, so you should realize, first of all, this block is experiencing in frame of reference of M1, that is kx, and apart from that, a pseudo force would be acting in this direction, and that would be nothing but M2 into A1, which is nothing but kx. Rather, you should kx upon m1 you should write. Okay, so m2 into kx upon m1. So what would be the equation of force on m2 in frame of m1? So F will be equal to this force plus this force over here, and when you take a kx common, so simply it would be minus kx into 1 plus m2 by m1. Okay, and F, you should write like F would be nothing but you can say m2 times a, m2 times a. So when rearranging a, you will be getting it as minus k into m1 plus m2 divided by m1 m2 into x, and we prefer to write it in this form. It is minus k upon mu into x, where you should realize mu is nothing but m1 m2 upon m1 plus m2, which is also known as reduced mass. Okay, so in this case, you should realize time period of the oscillation would be 2 pi root under mu by k. So that is two body oscillator. Okay, you can have several other setups of true body oscillator. Okay, and this would be the method. So like this we have done in frame of m1, we could have done it in frame of m2, we could have done it in frame of reference of ground. In C frame also we could have done, we could have applied energy method. The time period we would be getting in all those methods, that would be this 2 pi root under mu by k. So we have talked enough about the spring block system. So now let's talk a little bit about the simple pendulum, which is another very good example of SHM. So simple pendulum. Okay. So let's take the case of simple pendulum. Let's say we have a point of suspension, let's say O, which is say fixed. And from this fixed point, through a inextensible massless spring. We have suspended a bob of mass m, and the string length is L. Okay, so right now you can see the this block is in or this bob is in stable equilibrium position. Mg is acting downward, tension is acting upward, and Mg is equal to T. So that is in stable equilibrium position. So if we displace slightly, the system, okay, by let's say theta, or like linear displacement is, say this is x over here, obviously theta is equal to x by L, you can realize. Okay, so at this position now you understand there would be imbalance of forces. So Mg here is acting in this direction, so two component of Mg you can realize. Okay, so this is, let's say, theta, so that would be mg cos theta, and that would be mg sin theta. So you can understand, like, this would be the restoring component of the force over here, because this force mg sin theta is trying to bring this bob back to its stable equilibrium position. So F we can write it as simply minus mg sin theta. But since theta is very, very small, for a small oscillation I'm saying, so that would be approximately equal to minus mg into theta, and theta is x by L, so that would be equal to minus mg into x by L over here, and F is equal to ma, we are writing, so m gets cancelled, so a is equal to simply minus g by L into x. So time period obviously is 2 pi root under L by g, and this is one of the most famous equation, that is the time period of a simple pendulum. So here we have taken case when the point of suspension is stationary or fixed. Okay, so let's take another example when we will be having point of suspension accelerated. So if point of suspension is accelerated, okay, so let's take this example. So let's say this is point of suspension, and this is, say, accelerated in some random direction with acceleration a, and let's say a is making an angle beta from the vertical. So first of all, when you saw here, like, the vertical orientation of this pendulum was a stable equilibrium position, but now in this case this will no longer be the case over here. So like some stable equilibrium position of the bob would be something like this. Okay, so at this orientation, let's say length of this string is L. Okay, this bob is in equilibrium position, so let's balance the forces. Okay, so you should realize what all forces it would be experiencing at this orientation. Say this angle is alpha. Okay, so this here is mg, and apart from that you should realize, so this is we are doing the whole thing in the frame of reference of this fixed point over here. So a pseudo force would be acting in the direction opposite to this acceleration, so this would be pseudo force, let's say ma. Okay, and now we can resolve other the forces over here, like for example, um, along horizontal and along vertical, and this angle is beta, so you should realize this would be nothing but ma sine beta, and this would be nothing but ma cos beta over here. Okay, so we have resolved it, and now you should realize, let me draw one another diagram over here. So this component, vertical component of force, that is it is experiencing, that is nothing but ma or mg plus ma cos beta, so g plus a cos beta you can say, and this horizontal component is nothing but ma sine beta you can say. Okay, so the tension would be obviously along the resultant, and resultant of these two forces would be along this direction. Okay, or rather you can say that is mg effective. Okay, and this angle obviously is alpha over here. So two things we can find out, like what would be the value of g effective. And what would be the value of alpha over here? So I think these things are obvious. So G effective is nothing but G plus A cos beta whole square plus A sine beta whole square and the under root of this thing. And the alpha here is nothing but tan inverse A sine beta upon G plus A cos beta, that you should realize. So our objective was to find out the stable equilibrium orientation and the time period of the oscillation. So time period of the oscillation, time period, okay, like we know it for simple pendulum. So in this case it would be 2 pi root under L by G effective only, where the value of G effective we have already found out. So this is the case when the point of suspension is accelerated. Now let's look at one another case, okay, that is also very important question. See, we want to discuss the oscillation of pendulum when the string length is very, very large. So say oscillation of pendulum of very large length, of very large length. And you should realize, okay, when we are saying that very large length, how large it is. So let me tell you, that is comparable to radius of Earth. Okay, so that's quite huge. Okay, so how will we find out the time period of such a pendulum? So let's take this case. So let's say this is Earth. Okay, its radius is obviously R. Okay, and we have some pendulum, imaginary pendulum, which is suspended somewhere in space. It is hanging, let's say, at point P. Okay, and the string length is L. You should realize L and R here are comparable to each other. Okay, so this is the stable equilibrium orientation, because tension would be in this direction and mg would be towards the center, etc. Okay, so this is the stable equilibrium orientation. In order to find out the time period, what we can do, we can displace this bob slightly by some x. Okay, so this, at this orientation, we want to find out the restoring force. Now you should realize one thing: the restoring force is not downward, rather you should say it would be towards the center. Okay, because that would be gravity would be acting towards the center. So this is mg, and let's say the value of g is not varying much, we are assuming that. So now when we are resolving this mg in two components, sorry, I think my pen got hanged. So like when we are resolving mg in two mutually perpendicular components, one would be along the string and the another would be tangential to that curved path, or uh, uh, perpendicular to the radial direction. So in order to do that, okay, you should realize that how much this angle is, so this angle is not equal to this angle right now. So let's say this angle is theta 1, and this or theta, simply theta, let's say, and this angle is, let's say, phi. So you should realize this angle right over here, that is exterior angle of this triangle, so that is nothing but theta plus phi over here. Okay, so this component of restoring force F is nothing but you should rather say minus mg sine theta plus phi. Okay, and theta as well as phi both are small, so you can approximate it as minus mg into theta plus phi. Now look closely. Theta can be approximated as x by this L over here, and phi can be approximated as this x upon this radius over here, so x upon r. So when we will be substituting these, so F will be equal to minus mg, and theta we can write it as x by L, and phi we can write it as x by r. So rearranging f we can always write that is equal to ma minus mg into 1 by l plus 1 by r into x over here. So you should realize that m and m will get cancelled, and the relationship for acceleration we have got. So time period would be nothing but 2 pi root under 1 by g into 1 by l plus 1 by r over here. Okay, and that would be the time period of oscillation. Obviously you should realize that if l is much less than r, that is the general case we used to take, so then 1 by L would be much greater than 1 by R. So in this denominator, this 1 by R term we can ignore, and the formula would be still 2 pi root under L by G. So this is a general case scenario. Okay, so this is one of the situation. Another situation, let's take, that is one very famous problem. Let me talk about that. Okay, so let's say we have two walls. Okay, and let's say this is fixed ground over here and two vertical walls, and there are let's say the distance between these two walls is say a, and a bob simply is suspended by 2 points, let's say a and b, like this, something like this. Okay, this is the bob over here, let's say of some mass m. Okay, and the length of this spring is L1, and length of this string is L2 over here. And another part of geometry that is given in this question, that is definitely A, and this thing is given to you as B. Value of L1 and L2 is such that, in the question, that is L1 square plus L2 square is equal to a square plus b square. That is a very famous question. Okay, so if we displace this bob slightly into the plane of this paper and release, we have to prove that the subsequent motion would be SHM, and we have to find out its time period. So how are we going to do this? So now you should realize first of all that these points A and B are fixed. So can we draw a line AB here? Okay, line AB over here, and you should realize like this system would be oscillating about this axis. This would be oscillating about the axis AB. So in that case you should realize, okay, so effective length, see, if I draw a perpendicular from this bob on this line AB, so this here would be effective length. Okay, and since now this G is in downward direction, so over this other component would be balanced, and the G effective would be in this direction, that would be along the L effective. So this is the direction of G effective. So you should realize if this is G, its component, you should realize if this angle is some you can say beta, so G effective definitely is G cos beta. Okay, so it is clear the time period of oscillation would be nothing but 2 pi root under L effective upon G effective over here. So we have to find out the value of L effective as well as G effective. Okay, because we want to find out the value of beta over here, and what would be this. So how can we proceed here? So now you see, since a square plus b square is equal to L1 square plus L2 square, so using Pythagoras theorem, so this length will also be equal to L1 square plus L2 square is equal to AB square, we are saying. So this angle would be definitely 90 degrees. So if this angle is 90 degree, how much would be this L effective over here? So geometrically, you know that L effective would be nothing but you can say that will be L1 L2 upon root under L1 square plus L2 square, right? So that is one thing. Okay, and the another thing you should realize, if we substitute this in this equation, T is equal to 2 pi and L effective is nothing but L1 L2. Okay, and L1 square plus L2 square under root is also root under a square plus b square, and G effective we have learned that is nothing but G cos beta. Please understand, this is nothing but length AB. So how much would be AB cos beta? Like this angle beta, we are saying this is the angle beta. So obviously this angle here would be beta as well. So this angle here in would be beta as well. Okay, so you should realize that AB cos beta, this AB cos beta would be nothing but length A over here. So this into this, root under a square plus b square into cos beta is nothing but a over here. So you can simply write it as 2 pi root under L1 L2 upon G into a over here, where a is this length, and so this would be the time period of oscillation of this system. Okay, of small oscillation, for small oscillation only. So I think today's time is up. Okay, so that's it for today. And